This is Unit 7, Video 11, Buffer Calculations. Now that we understand what a buffer solution is, it's a conjugate acid-base pair, we can do a stoichiometry calculation and figure out if we add an acid or a base to the buffer, what are the concentrations after the reactions occurred. So it's simply a molarity-based stoichiometry calculation of solutions. So we've got a problem here. We have a buffer, 50 milliliters of a buffer. The buffer is 0.25 molar HF and 0.25 molar NaF. Now, not all buffers have to be exactly the same solution concentration of the two components, but a lot of times you'll see that. Obviously, if I notice the sodium is a spectator ion, I can see my conjugate acid-base pair is HF and F minus. Okay? We have this solution, and we're going to add 20 milliliters of a 0.1 molar sodium hydroxide solution. So we're pouring in. So let's just draw over here. We've got a useless marker. All right, so here's our beaker, and in this we've got HF and F minus. There's 50 milliliters of this. Okay, and they're floating around. They're our buffer solution. So now we're going to take 20 milliliters of NaOH and pour it in. Now, obviously, when we're done, we're going to have 70 milliliters. They're going to add up. We're going to get 70 milliliters. Since we're adding a base, you would immediately look at your buffer and ask which component is the acid component of the buffer. Every buffer has an acid component and a base component. So the acid component clearly is the HF. So let's write that reaction, or the reaction between sodium hydroxide and hydrofluoric acid. So we're going to go NaOH plus HF. These cations are going to switch, and we're going to get NaF plus H2O. Okay, obviously NaF is going to be an electrolyte, and that's going to be liquid. So there's our reaction. It's 1 to 1 to 1, so it's balanced as written. Most of the time these reactions will be that way. All right, now we're going to write what we call an ICE expression. Okay, I stands for initial, C for change, E in chemistry is equilibrium. We can think of it as kind of the end right now, and then we can come back later and understand what equilibrium is all about. So we want the initial moles here. These reactions occur mole to mole, not molarity to molarity, mole to mole. Okay? So, first thing we're going to do is calculate the moles of HF. That's going to be 50 milliliters times 0.25. I can come over here and say, okay, 0.05 liters times 0.25 molar is going to give me 0.0125. And that's the number of moles. So remember, molarity times volume equals moles. So my initial moles of HF is 0.0125. Now, since NaF has the exact same molarity, I can do the calculation again, but it's the exact same calculation. It's 50 milliliters times 0.25. So it also initially has 0.0125 moles. So we're putting the initial moles here across in the I slide. Now, NaOH was 20 milliliters of a 0.1 molar solution. Move over here. So we're going to have 0.02 liters times 0.1. Multiply those together, and we're going to get 0.002. So my initial moles of sodium hydroxide is 0.0020. Actually, 00 would be the right number of significant figures. Okay, so let's go through and look at the change. These two are going to react with each other. Bases react with acids. The limiting reactant is the sodium hydroxide. So we're going to completely neutralize the sodium hydroxide in this reaction. So minus 0.002. Well, when that happens, it's going to take out an equal number of moles of HF since the reaction's 1 to 1. So this is going to be minus 0.002. Reactants make products. That's what they do. So if we have 0.002 moles going away, it has to be making 0.002 moles of the two NaF and H2O. We don't really care about the H2O. We want to know the components in the buffer. So this is going to be 0.0020, but we're adding on this side because we're making products consuming reactants. Well, now we can subtract that. So when we're all done, at the end, we're going to have no base whatsoever. Okay, it's completely gone. Now we can subtract this, and we're still going to have some acid left over. That's going to be 0.0105 moles. So it's lost some, but it's still a buffer solution. This is going to gain some. It's going to be 0.0145 moles. Okay, so we can see the buffer's done its job. It's completely neutralized the base. Now we've got some new values here. We want to calculate the new concentrations because that's what the problem really was asking. New concentrations. Let's start with HF. HF is going to be equal to the moles, 0.0105, divided by the liters. Now, at the end, the new concentrations, the liters are 70, not 50. So we're going to divide this by 0.0700 liters. When I do that, I get 0.150 molar. So my HF concentration has dropped, but it's still there. NaF, we're going to have 0.0145 moles of the NaF, and it's also in the 70 milliliters. So we're going to divide that by 0.07 liters, and we will get the new concentration of 0.207 molar. So there's my two components. I still have a buffer solution. They're no longer equal, but that's not a requirement of a buffer solution. So they don't have to be equal, they have to both be there. That's the key.